Hello and welcome to another Algebra 1 video by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 3, Lesson 7 on the average rate of change. So I want to get right into this and discuss what average rate of change is, why we need it, and how we calculate it. Let's do this. So rate of change, right? How fast something is changing. Functions, right, as we know, are rules that give outputs when we supply them with inputs. We often, though, want to know how fast the outputs are changing when the inputs change. And this is what's known as rate of change. Now, sometimes we refer to it as average rate of change because, if you kind of think about how fast your car is going, right? You can kind of think about well, I know kind of on average how fast it's going. Sometimes it's going a little faster, sometimes it's going a little slower, but maybe on average I'm going 60 miles an hour, right? So we typically throw in that word average rate of change because we can't get what's called instantaneous rate of change. That you have to wait until you take calculus to think about. But let's kind of jump right into exercise number 1 and talk about what average rate of change is. The doors to a movie theater open 15 minutes prior to the movie starting. The table below shows the number of people who have entered the theater as a function of time, measured in minutes after the doors have opened. So I want to make sure that you really understand how to read this function that's in a table. What I'm saying is, right when the doors open, 0 minutes, right? 0 people are in that movie theater. After 4 minutes, if you counted all the people that were in the movie theater, there'd be 32. After 6 minutes, if you counted all the people that were in the movie theater, there would be 54, right? So that's the idea, right? This is the number of people that are literally sitting in the movie theater after this many minutes since the doors have been opened up. So now let's take a look at letter A. Find the value of n of 9 minus n of 4. What does this represent in the context of this problem? All right, well, we've done this type of calculation repeatedly with function notation. So I'd like you to pause the video now and go ahead and figure out what the answer to that calculation is. By the way, I probably should have mentioned that in this lesson, we're going to be doing some kind of messy calculations that you're not going to want to be able, you're not going to want to do by hand. You're going to want to have at least, a scientific calculator or your phone's calculator or something handy to be able to help you with some of these calculations. This one is fairly easy, right? N of 9 minus n of 4. Let me just make sure I have those individual values, right? N of 9 is right here. That's 102 people. Right, n of 4 is right here, that's 32 people. And actually now subtracting these is pretty easy. N of 9 minus n of 4, which is 102 minus 32, is equal to 70 people. Now, even more importantly, though, is that interpretation, which I've literally left myself no room to write down, right? So let's just talk about that interpretation because it is critically important to understand, right? What that 70 people tells you is that between 4 minutes and 9 minutes, between those two times, right? If you kind of, if you just looked between 4 and 9 minutes, 70 people entered the room. Let me see if I can fit that in a real small way. Between 4 and 9 minutes, 70 people entered. Wow, that just does not look like the word entered whatsoever. Entered. Okay, and that is critical. It's not that after 9 minutes there's 70 people in the room. Right? It literally means if you only counted the people who walked in that door between 4 minutes and 9 minutes, it would be 70 people. Now let's look at letter B. At what rate did people enter the theater from 4 to 9 minutes? Show how you found your answer and use appropriate per rate units. Right? All rates have units that are kind of like per. Miles per hour, cookies per bag, calories per soda. Always rates have this many things per this one thing. So what I'd like you to do is pause the video now and see if you can think about how fast or what the rate was that people entered the room between 4 and 9 minutes. Pause the video now. Well, this is really all about understanding division, right? 70 people entered the room over 5 minutes. So if I divide 70 people by 5 minutes, now I'm going to pull my calculator out really quick, right? That's why we want to have it. 70 divided by 5. What I find is that there are 14 people per minute who have entered in to the movie theater, right? If I take how much has changed over that time and I divide it by how much time has elapsed, I find out how many people per minute were entering into the theater. And I hope that makes sense to you. It's just a rate. So let's take a look at letter C. On average, were people entering the theater faster between 4 and 9 minutes, or between 9 and 15 minutes justify your answer? All right, well, keep in mind, right, we know already how fast people were entering between 4 and 9 minutes. They were entering at a rate of 14 people per minute. You can kind of think about that as miles per hour. How fast were they coming in? 14 people per minute. Okay, so now the question is, for you, how fast were they coming in between 9 and 15 minutes? Pause the video, see if you can figure that out, and then tell me, over which time interval were they coming in faster? Well, the first thing I really need to do is figure out how many people came in between 9 and 15 minutes. To do that, right, I look at the 9-minute mark and the 15-minute mark, right? And we know that we have 150 people minus 102 people, right? So that's 48. So 48 people came in between 9 and 15 minutes. All right, but that's just how many people came in. That's not how fast they came in. That's just simply how many people came in between 9 and 15 minutes. If I want to know how fast they came in, I'm now going to take that difference, 48 people. I'm going to divide it by how much time elapsed. Well, how much time elapsed? I can do that by doing, 15 minutes minus 9 minutes. And of course, that's 6 minutes that have elapsed. So that's going to be 48 people divided by 6 minutes, and that's going to be 8 people per minute, right? So between 9 and 15 minutes, 8 people per minute came in, right? And between 4 and 9 minutes, 14 people per minute came in, so they were coming in faster. So they were coming in faster from 4 to 9 minutes, right? The speed with which people were entering was faster, right, over this interval, right, than they were over the interval 9 to 15, right? And that's it. It's just a rate. It's how fast the function is changing or how much the function has changed compared to how much the input has changed. And you do that, as you always do with rates, by using a ratio in the form of a fraction. And that fraction, of course, then is a division problem. So now let's formally define what we mean by average rate of change. What we found in the last exercise is called the average rate of change. Specifically, we were finding the average rate with which the number of people entering the theater was changing. Ooh, that was wordy. But let's talk about the average rate of change, right? So the average rate of change of a function, f of x, right? The average rate that it changes when x goes from a to x goes to b is given by simply doing f of b minus f of a, right? Think about that. We did n of 9 minus n of 4 divided by b minus a. Now, that fancy formula really boils down to one thing. We're finding out how much the y values have changed over that domain interval divided by how much the x values have changed over that domain interval. Or better yet, you're finding out how much the output has changed divided by how much the input has changed. Now graphically, this is kind of cool. Let me just make sure you sort of understand this from a graphical perspective, right? So here's that average rate of change. Those little triangle symbols, which you may have seen back in middle school when you were doing slope calculations, these little triangles, you'll see these a lot in math. These literally stand for the word change in. All right? So, and it's actually the Greek letter delta, the Greek letter delta. So you'll hear a lot of math teachers say delta y divided by delta x, the change in the y divided by the change in the x. And it's really cool. Remember, functions respond to their inputs. So the idea is, I got, x equals a and some output f of a, and I have x equals b and some output f of b. Right? And I can calculate when x goes from a to x goes to b, I can calculate how much x has changed by just doing that subtraction, b minus a. I can then tell how much the y has changed by doing f of b minus f of a, and then I just divide those two changes, right? Just how much did y change divided by how much did x change. In the last problem, we were looking at how much did the number of people change divided by how much did time change, how many minutes went by. So, last problem, we had this really nice, just kind of, very practical example of what was going on. Now let's look at one that's a little bit more just kind of abstract. Let's take a look at exercise number 2. For the function f of x equals x squared plus 5, find its average rate of change over the following two intervals. First, we want to do it as x goes from -1 to 5, and then we want to do it as x goes from -6 to 4. Now, with a formula like this, I'm going to be very just kind of here's how you do it sort of thing. So what I'm going to do is the first thing I want to know is I'd like to know what the y values or the outputs are at these endpoints. So the first thing I'm going to do is I'm just going to figure out, well, what is f of -1, right? And I'm going to do that obviously by just plugging it into my formula. -1 squared is 1, 1 plus 5 is 6. Then I'm going to figure out what f of 5 is. F of 5 is 5 squared plus 5, which is 25 plus 5, and that's 30, okay? And now what I want to do is I want to figure out what f of 5 minus f of -1 over 5 minus -1 is. And again, I want to kind of emphasize what this calculation is doing. The calculation in the top is simply finding the change in these function values. So that's 30 minus 6. And the denominator, right, which is 5 plus 1, that is telling me how much the x values have changed. Now I'm going to finish this calculation in just a moment, but again, I want you to understand, right? It's very simple, right? When x went from -1 to 5, y went from 6 to 30, so it increased by 24 units. On the other hand, as x went from -1 to 5, x increased by 6 units, and therefore when I do the final division, I get an average rate of change 24 divided by 6, which is 4. If there really were units in this problem, the units would be 4 units of y per 1 unit of x. 4 units of y per 1 unit of x. That's what that calculation tells me. I'd like you to pause the video now and see if you can do this calculation in letter B. I know it's kind of new, and so is all the function notation and all that, but take a shot at it and then we'll go over it. All right, just like before, I want to figure out what my y values are at the two endpoints of the domain interval. All right, so f of -6 is going to be -6 squared plus 5. That's 36 plus 5, and that's 41. F of 4 is going to be 4 squared plus 5. That's 16 plus 5, and that's 21. All right. Therefore, I'm going to have f of 4 minus f of -4, all divided by 4 minus -4. All right, and that's going to be 21 minus 41, all over 4 plus 4. That's going to be -20 divided by 8. And again, before we kind of move on and do that final calculation, I just want to talk about this for a minute, because there was a little bit of a complication here, right? As x goes from -6 to 4, y actually decreases, right? Y goes from 41 to 21, which is indicated by a -20 there, okay? On the other hand, as x goes from -6 to +4, for some reason I've got 4 and 4 down here. That doesn't make any sense. Why in the world I did that, I don't know. I apologize for that. That should be a -6 there. Oh my, that should be a -6 there. And this should be a 10 there. And a 10 there. So let's talk about that again. As x goes from -6 to +4, thankfully I caught myself. As x goes from -6 to +4, x has increased by 10, right? Y decreased by 20, x increased by 10, and overall the rate is -2. And again, if it had units on it, right, then the units would be -2 units of y per 1 unit of x, meaning that for every 1 unit that x increased, y decreased by 2. Here, for every 1 unit of increase in x, we got y increasing by 4, all right? So average rates of change can be positive when the function is increasing, and average rates of change can be negative when the function is decreasing, as it does here. Now, some students might say, well, could I flip-flop the numerator and the denominator? Could it have been f of -6 minus f of 4 over -6 minus 4? And the answer is yes, absolutely. In that case, you would have gotten +20 divided by -10, and you still would have gotten -2. Here you would have gotten -24 divided by -6, which would have still been +4. But you'll find, for me at least, I will always try to keep the change in x positive. I will always move from right to left so that I can be thinking about, as x increases, what is y doing? So I will always keep this, every time in my calculation, that denominator is going to end up positive. I am always going to do the x on the right minus the x on the left, and the y that goes with that x minus the y that goes with that x. All right, I would suggest you do the same. We always want to be thinking about what is the function doing as its input gets larger. Is the function going down or is the function going up? All right, let's keep going. Exercise number 3. The function h of x is given in the table below. Which of the following gives its average rate of change over the interval x greater than or equal to 2, less than or equal to 6? All right, well, this is really nice. Here we're given this function in table form. It should be pretty easy. Pause the video now and see if you can figure it out. All right, well, again, the formula at least would just be h of 6 minus h of 2 all over 6 minus 2. Now this is pretty easy because h of 6 is sitting right here. That's equal to 3. Minus h of 2, that's equal to 9, right? All over 6 minus 2. That gives us -6 over 4. And again, I'm going to just keep harping on this as much as I can. When x increased by 4 units, right? X increased by 4 units as it went from 2 to 6. Y decreased by 6 units as it went from 9 to 3. And we're seeing that right here, right? The top is always the change in y, or the change in the function's values, divided by the change in the x values. Now, if I look at my answers, right, -6/4 isn't one of the 4 answers sitting there, and that's simply because it's not a fraction in reduced form. If I divide numerator and denominator by 2, I get -3/2, and that's choice 1. All right? Again and again and again, average rate of change is telling you how is the y responding to a change in x. And really we could interpret this one as for every 2 units that x increases, y decreases by 3 units. By the way, if this is sounding a little familiar, if you're saying, I feel like I've heard of this before and I feel like I've done this calculation before, you have. What we're really doing is we're doing the calculation for the slope of a line, the change in the y values on the line divided by the change in the x values on the line. The difference here is that it doesn't have to be a line. It could be any function whatsoever. Let's keep going with average rate of change. All right, now in applied problems, which is where I really like to do average rate of change, and the first example was like that, the rate of change formula also involves units that can be helpful when you want to think about your answer. So let's take a look at exercise number 4. Skylar is selling glasses of lemonade. The function g of t equals t squared plus 4 divided by 2 models the number of glasses she has sold, g, after t hours. What is the average rate at which she is selling lemonade between 2 and 8 hours? Include proper units in your answer. Great. So again, you always want to make sure you understand what the function that they gave you tells you, right? So g of t equals t squared plus 4 over 2. If I took like my t equals 2, let's say, and I plugged it into that formula, just so that we can really understand what the formula is telling us, I'd have 2 squared plus 4 divided by 2, which is 4 plus 4 divided by 2, which is 8 divided by 2, which is 4, right? All that tells us is after 2 hours, right, that Skylar has sold 4 glasses of lemonade, which doesn't sound like she's doing all that well with her lemonade stand, but if you've ever had a lemonade stand, sometimes it starts off slow until the word of mouth kind of spreads it around, right? But make sure you understand that, right? After 2 hours, Skylar has sold 4 glasses of lemonade, right? Likewise, let's figure out what g of 8 is, right? G of 8 will be 8 squared plus 4 divided by 2, which will be 64 plus 4 divided by 2, 68 divided by 2, which is 34. In other words, after 8 hours, Skylar has sold 34 glasses of lemonade. All right, depending on how much she's selling them for, maybe that's a little bit better. The question becomes, right, what is the average rate at which she's selling the glasses of lemonade between 2 and 8 hours? See if you can finish this off. Well, again, just common sense, right? Forget about the formula g of 8 minus g of 2 over 8 minus 2, right? How many glasses of lemonade did she sell from 2 to 8 hours? Well, she sold 30 glasses, right? Because she had already sold 4 glasses by 2 hours, then she had sold 34 glasses by 8 hours, so she must have sold 30 glasses of lemonade between those 2 moments in time. How much time elapsed? 6 hours. So she sold 30 glasses of lemonade over 6 hours. She must have sold 5 glasses of lemonade per hour on average. But, the way that the formula looks, right? The way the formula looks is g of 8 minus g of 2 over 8 minus 2. Just trying to get this a little bit out of the way, right? Which is 34 minus 4 over 6. 30 over 6, which is 5 glasses per hour, right? And you can really track those units, right? The units of the numerator are glasses. I couldn't quite fit that in, right? 34 glasses minus 4 glasses is 30 glasses. 8 hours minus 2 hours is 6 hours. So I have 30 glasses divided by 6 hours, which is 5 glasses per hour, right? Just like those people entering the theater, right? People per minute. Here we got glasses of lemonade per hour. Okay. Now, we should be able to also think about average rate of change if we know the average rate of change and we know a beginning value for our function. We should be able to then calculate an ending value as well. Let's take a look at exercise 5, sorry. The temperature of a liquid that is being heated has an average rate of change of 12.8 degrees Fahrenheit per minute from t equals 3 minutes to t equals 8 minutes. If the liquid's temperature at t equals 3 minutes is 72 degrees Fahrenheit, what is its temperature at t equals 8 minutes? All right, I think that there's probably plenty of you out there that can actually figure this out, even without any discussion about average rate of change. I bet there's some of you out there that can figure this out. So I'd like you to pause the video now. You might need to use that calculator, right? But pause the video now and see if you can figure out what the temperature is at 8 minutes given all the other information in the problem. All right, well, here's the sort of like very formulaic way of doing it. And then I want to talk about like maybe a more common sense way to do it. You know, formulaic, common sense. All right, I have to kind of invent a function here for the temperature. I think I'm going to call it capital F for Fahrenheit, right? So what do I know, right? What I know at this point in time is that capital F of 3, right, my Fahrenheit temperature at 3 minutes was 72 degrees Fahrenheit. Right? I also know that f of 8 minus f of 3 all over 8 minus 3, right? That's my average rate of change. My average rate of change is equal to 12.8 degrees Fahrenheit per minute, right? So now I can do some substitution, right? I can say f of 8 minus 72 all divided by 5 is equal to 12.8. Right? So far, all I'm doing is just using, here's my average rate of change formula. I just know the average rate of change now is 12.8. That decimal point is never big enough on here. Is 12.8. So f of 8, I don't know, minus 72, all divided by 5 is equal to 12.8. If I want to now solve this for f of 8, think about this. This is just solving an equation, right? I had 72 subtracted from it, and then I divided by 5, and I got 12.8. So I'm going to undo that by multiplying by 5, right? I'm just going to undo by doing those order of operations. This is where I think I need my calculators. Oops. I don't know what just happened there, but I've got 12.8 times 5, which is 64. So now I'll have f of 8 minus 72 is equal to 64. And now I'll add 72 to both sides, right? And I'll find that f of 8 is equal to 64 plus 72. Can't believe I just did that on a calculator. And I'll get 136 degrees Fahrenheit. Right? So if you got 136 degrees Fahrenheit, you got this correct. Okay? Oh, that's what happened. This stuff all kind of moved. Very funny. All right, now that's just like, oh, let me take the average rate of change formula and just plug everything else in. Right? On the other hand, right, if you were doing this in a common sense way, you know, think about it. If I told you that you were, 50 miles away from Albany and you were driving away from Albany at 60 miles an hour, and I asked you how far away you were after 2 hours, you'd probably go, well, going 60 miles an hour for 2 hours, I would drive another 120 miles, and then I'll just add that onto the 50 miles that I started away from Albany, and that's how far away I was. And that's one way to do this problem. One way to do this problem is to just say, hey, look, I've got 12.8 degrees Fahrenheit per minute times 5 minutes, right? And that is 64 degrees Fahrenheit, right? So I could just literally take my rate, 12.8 degrees Fahrenheit per minute, and multiply it by 5 minutes, because that's how much time has passed between 3 and 8 minutes. That 64 degrees, right, is this thing sitting right up here. And I could say to myself, well, that's how much the temperature went up, because the temperature is going up by 12.8 degrees Fahrenheit per minute for 5 minutes. So the temperature went up 64 degrees Fahrenheit, and therefore I'm going to take my starting temperature, 72 degrees Fahrenheit, add on how much it went up over that time, and I could say it's at 136 degrees Fahrenheit. And I would almost rather have you do it that way. The only thing that's a little bit tricky about this approach is you'd have to watch out a bit if the rate was negative, right? If whatever you were dealing with was decreasing instead of increasing. All right, let's take a look at one last problem. Okay, when we compare average rates of change of two functions, and you're oftentimes asked to do this on standardized exams and things like that, we should be ready to compare those if the functions are given in different forms. And remember, functions can come in the form of equations. We saw that in exercise 2. It can come in the form of tables. We saw that in exercise 1 and in this exercise. And they can also come in the form of graphs. So let's take a look at exercise number 6, where we try to figure out which function has a greater average rate of change. Given the two functions shown below, which has the greater average rate of change from x equals -4 to x equals 6? Show calculations that lead to your answer. Okay, great. So one of these two functions is changing faster from x equals -4 to x equals 6. I'd like you to pause the video now and see if you can figure out which one's got the faster average rate of change. I shouldn't say the faster average rate of change. An average rate of change is a number. Numbers aren't fast, they're just numbers. Which one has the greater average rate of change? Well, let's first take a look at f of x, right? So for the function f of x, all right, the first thing I think I want to know is I want to know my two function values. Like what is f of -4 and what is f of 6? Well, f of -4, I can go over here, right? I've got the point -4, -1. So f of -4 is -1. Then if I go out here to 6, I've got the point 6, 4. So f of 6 is equal to 4, right? So now I can do a little bit of my change in f divided by change in x, and that's going to be 4 minus -1 all over 6 minus -4. Come on. And that's going to be 5 divided by 10, and that's going to be 1/2. So the average rate of change of f of x between those 2 points is equal to 1/2. For every 2 units that x increased, y increased by 1 unit. Now g of x is going to be a little bit easier because, boy, it's just right in the table, right? Not a lot I have to do there, right? For g of x, here's g of 4, and here's g of 6. So now I'm gonna go almost directly to that calculation. G of 6 minus g of -4. I keep doing that. G of -4 all over 6 minus -4. Well, that's going to be 15 minus 9 all over 10. And that's going to be 6 over 10, and that's 3/5. Right? For every 5 units that x increased, y increased by 3 units. So now the question is just which one's got the greater average rate of change, and I hope that when you all look at these two, you realize that 3/5 is larger than 1/2. Okay? So g of x has the greater average rate of change. Right? 3/5 is greater than 1/2, so g of x has the greater average rate of change. Not by a lot. We're talking about 0.5 versus 0.6 in terms of decimals, right? But it's definitely larger. All right, so today's topic was amazingly important. We're going to see it come up time and time again in this course, here and there, because we're going to be studying varieties of functions. We're going to be oftentimes wanting to calculate how fast the outputs of a function are changing as the inputs change, all right? We do this sort of on average because the best we can really do is say, all right, well, I know what the function's value is here. I know what the function's value is here. I can calculate how much that function has changed. I can calculate how much the inputs have changed. I can then divide the two and come up with that rate. In real-world practical problems, this comes up all the time, right? How many cups of lemonade per hour, how many feet per second, et cetera, et cetera. And we're going to get a nice workout with this on the next lesson when we talk about motion and speed. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.